Hello, let's get on time and going. My name is Jianwu Wang, a professor at the University of Maryland, Baltimore County, and the co-PI for the iHARP Institute. We have six talks for this morning before the lunch. So we'll be on time, so we can have lunch on time. Each of them is yeah. So each talk is 15 minutes, including Q&A. So please give finish your talk around 10. Sometimes you can be 12 or 13. I will stand up if it's getting closer, and we have some discussions. So you can see every talk is a lot a long list of members. So it shows the interdisciplinary team for each project, where we try to bring both data science and political science researchers. First one will be given by Ziqi from University of Colorado Boulder. Go ahead.
Thanks. Yeah, hi everyone. My name is Ziqi. I'm a PhD student from CU Boulder, and today I'm going to present the result of my first project about coupled climate edge sheet modeling. And because my current this is part of project 9, and because my current project is part of project 7, so I will also give a brief overview of the work has been done by project 17. Okay, so. Um, so as this map shows the DEM of the Greenland ice sheet, we can see it's surrounded. It has at the margins it has steep topographic gradients, and also it's surrounded by these jagged mountains. And the previous study has showed that in lower resolution, like 1 to 2 degree climate models, because of the smooth topography, there are too many moisture penetrating into the interior and cause a positive precipitation biases there. So, and also the ablation zones, which has where the ablation is larger than accumulation, sometimes can be as narrow as tens of kilometers. So we need a fine resolution to resolve these ablation zones and the topographic gradients. And also because of the melting of Greenland is caused by both atmosphere warming and oceanic warming and the interactions between the components. So we also need a coupled framework. So that lead to our modeling strategy of using the fully coupled CSM2. And within the configuration, we also have a dynamic Greenland ice sheet model, CISM2. And the right plot shows the coupling scheme of this model. So basically, the ice sheet model receives the surface mass balance from the land component and update the topography to the atmosphere and also the boundary to the land. And we note here that there's only one-way coupling between the ice sheet and the ocean. It doesn't include the warmer ocean impact on the glacier front. So to achieve higher resolution, we use this variable resolution grade that has a quarter-degree regional refinement over the Arctic region. And this variable resolution grade is applied to the atmosphere and land components. And there are some other parameters of this model framework. And by using this model, we try to answer two research questions. So first is, what's a multi-century Greenland ice sheet evolution with a focus on ice sheet climate interaction? And also the second one is, what's the added value of this regional enhanced resolution? So today I'm going to focus on only the second question. We branch off the simulation from a long spin-up simulation and first run a pre-industrial run of 180 years until the ice sheet achieved near equilibrium state, and then started this idealized warming scenario in which the atmosphere CO2 increased by 1% per year until reaches 4 times the pre-industrial value and continues for another 210 years. And the second panel shows the temperature rises over Greenland, Arctic, and global. And we compare this variable resolution run named Arctic to other two 1 degree simulations called F09. And because they share common features, so today I'm going to only include one of them. Okay, the result, we first can compare several time series of several important variables between the variable resolution run and 1 degree runs. So the variable resolution run is showing orange. And we found that the major difference between the variable resolution run and the 1 degree runs is that the Arctic run has a smaller melt increase. Is negative here, but that means more negative means more melt. And this smaller melt result in a slower decrease of surface mass balance, as volume, and finally result in a smaller sea level rise contribution. And if you look at the spatial maps, we can see the bottom, the medium panel shows their melt differences over the average over the 350 years. So we see the smaller melt of the Arctic run mainly happens at this sloping, this slowly, gently sloping surfaces in the western and northern basins of the Greenland ice sheet, also called the transition zones. And this pattern causes the dominates the ice thickness change pattern, with the Arctic run has a smaller thinning over these blue regions. And the question is, what causes smaller melt of the variable resolution simulation? And by we first look at the cloud condition differences and the downward radiations. So we see by looking at the difference of cloud fraction and cloud liquid water path, we see the Arctic simulation has a smaller cloud fraction and liquid water path around these boundaries. And this results in more downward shortwave radiation in these regions. And the differences in downward longwave radiation is also is the impact by the cloud, also impacted by the lower free atmosphere temperature over the Greenland ice sheet. And we continue to look at the net shortwave and longwave radiation differences. We see at the second line, the net longwave radiation follows the same similar pattern of the downward longwave radiation, but for net shortwave radiation, we found that despite we have more downward shortwave radiation for the Arctic run, we found that in these blue regions, we found smaller net shortwave radiation. So that means in the Arctic run, the surface albedo decrease is smaller compared to the 1 degree simulations. And it could be because of a weaker albedo feedback. So in these regions. And yeah, this right plot shows the total melt energy pattern difference pattern, and we can see it's a combined row of the differences of net shortwave and longwave radiation. And we quantify the albedo feedback by dividing the change of net shortwave radiation by the change of near surface air temperature. And they can see in this left panel, we found all positive values for this albedo feedback over the ice sheet. And compared to the 1 degree resolution run, we found a smaller, weaker albedo feedback in these transition zones. And we think this is the reason for this is because of the topography differences. So in this right plot, it shows compares the initial surface elevation of this 1 degree grid simulation and the Arctic simulation and their differences. So we can see the Arctic topography has higher elevation in the interior of the ice sheet, but lower elevation at the ice sheet boundaries. So if we plot a transect conceptually, for example, in the western Greenland, it will look like this. So the Arctic topography have a steeper surface slope. So this steeper slope will favor slower expansion of the ablation zone. And we test our theory by first look at this elevation cumulative area relationship. So in this plot, a steeper slope means with the same amount of elevation increase, more surface area is exposed. So and the dotted line, the dashed line here is represent year 0, and dotted line is year 350. So we can see in both these time periods, the orange line, which represent the Arctic simulation, has a less steep slope, which means it may favor, so we will expect it has a slower ablation zone expansion. And then to test this, we plot the scatter plot of annual equilibrium line elevation and ablation area relationship. So the equilibrium line is the line that separates ablation area and accumulation area. So we see this pattern is similar to this elevation cumulative area relationship. So that confirms our theory that with the same amount of equilibrium line altitude rise, less ablation area exposed in the Arctic simulation. Okay, so for conclusions, we found this slower melt increase in the Arctic refined simulation compared to lower resolution runs. And this is because the steeper topography of the ice sheet favors slower ablation zone expansion and resulting in this weaker albedo feedback. And as a next step, my work is part of this Project 7. I use causal inference to the data from this coupled model to study about the relative importance of surface energy balance terms on surface melt. And and also see their potential changes in a warmer climate. And basically we found increasing role of turbulent heat fluxes in a warmer climate and a dominant role of net shortwave radiation. And if you're interested, please come to my poster in the afternoon. And Sahara from UIBC and I also are summarizing a causal graph related to Greenland surface melt and from literatures, and it's ongoing work, and this will help us to evaluate our causal inference result. And we are also interested not only in learning the causal relationships, but also to quantify the impact of the processes on Greenland melt. So in this work, our group member developed this machine learning-based causal inference method. And you can see in this central plot, it shows the model predicted melt, summer monthly melt for observed data in red and intervened data in blue. So the intervention here is increasing the Greenland blocking index by 15%. And we found a response of the ice sheet of 1.5 kilogram per square meter per month increase of the surface melt. And this is another work led by Sahara Ali. And so here in this work, we extend the capability of the model by not only look at the time series, but also spatial temporal data. So here the aim is to detect which region is impacted by the intervention, which is decreasing the downward long wave radiation in this Laptev Sea and East Siberian Sea. And so the second plot shows the response of the sea ice in this region. So by decreasing the downward long wave radiation by only 5%, we found that there's an increase of the sea ice concentration by 20 to 30%. And also in this sea ice anomalous years, like 1990 and 2003, we found this impact on CS concentration also extend to neighborhood regions outside of this region of interest. And if you are interested, please stop by the poster of Dr. Jianwu Wang in the afternoon. Okay, and that's my references, and thanks for your attention. I will happy to answer any questions. Thank you. Andy.
Thanks for the talk. I was curious if I got that right. All the three simulations started in pre-industrial.
Yes.
And you looked at the elevation feedback. So I'm kind of interested, how close are your three simulations at present day with respect to the observed DM? And could you explain some of the differences that that you saw, or just because each simulation had a different surface elevation at present day, and you started from like a different starting point?
Yeah. So our simulation is false. So we have this pre-industrial simulation and idealized warming. So we don't have a present day scenario. But for this it's this S volume plot. You can see the initial state for this idealized warming scenario. There have a different S volume, and also the map shows there have different surface topography, and that is because when we change the resolution of the atmosphere, we have to like do some tuning to bring the top of atmosphere radiation to balance, and after the tuning processes, the ash sheet volume already changed. So that's why it has a different initial ash volume. So here we compared to these two simulations, and bounded by the two 1 degree run. So we want to, so this can test that whether the initial volume is smaller or larger of the low resolution run to the Arctic run. We still found this slower as volume decrease compared to the lower resolution run. So for the robustness of our theory. Yeah.
Thank you.
Thank you.
Now we have to